dimethyl-cyclohexane. This is planar arrangement. Both the methyl at same site, hydrogen same site. So this one is cis. Plane of symmetry. But these two carbon are chiral carbon. How? This carbon is attached to 4 different groups. One is methyl, one is hydrogen, one is CH2, then CH, CH2, then CH. Another side, this is CH2, CH2. So these two sides are taken as 2 different groups. 2 different groups, 2 different groups. So this carbon will be chiral and this carbon is again chiral. So this cis arrangement have 2 chiral carbon, but have a plane of symmetry. That's why this form is mesoform, which is optically inactive. Its mirror image will be identical, superimposable. But we'll see some other configuration like trans arrangement. This one is cis dimethyl. If it is trans dimethyl, both the methyl group will be on opposite side of a ring. As you have seen in chair conformation, this one, 1 and 3 position, this one is cis 1,2 dimethyl, but in trans this will be on opposite side. See, dotted line. Methyl and H are on the same side. Methyl and H are on the same side. Methyl and H are on the same side, but methyl are on the opposite side. So this one is trans. But there is no plane of symmetry because we can't divide it into 2 equal halves. One side there is hydrogen, on the other side it has only some different group, methyl. So trans is optically active. It will have 2 optical isomers. One is dextro, other is levo. Dextro and levo are non-superimposable mirror images. So trans arrangement have chirality. Dextro is right hand side rotatory isomer, as you did in optical isomerism, and this is levorotatory, negative sign for opposite rotation, left hand side rotation of plane polarized light. Now how can we draw their chair conformation? First, for cis arrangement, chair will be like this. Now substituents are at first and third position. This is the first position, axial. Second, equatorial. Then axial. This one is equatorial. At first carbon, methyl. In second position, third position, again there is methyl. Both the methyl are at axial position. Rest of the carbon they have hydrogen. This is cis arrangement and the most unstable arrangement, because two methyl bigger atoms are at axial position. They are comparatively close. Will have more repulsion with each other as well as with other hydrogen. We can draw other chair, this chair, where all axial position will be equatorial one. This methyl is at equatorial position. This is the second carbon. This one is the third carbon. Again, methyl is at equatorial position. And this equilibrium constant will be more than 1. This is cis arrangement, where the second one is most stable. First one is least stable. So in 1,3-dimethyl-cyclohexane, cis arrangement is more stable than trans conformation. Whereas in 1,2-dimethyl, we have seen that trans one is more stable than cis one. You can draw its trans arrangement also, like this. This is cis arrangement and the trans one. Methyl, this methyl is on the opposite side. First bond having different groups, so it is trans. Other chair, again one of the methyl will be at axial, one will be at equatorial. So both the trans have same stability. Equilibrium constant will be 1. But both the trans are less stable than one of the cis conformation. So in 1,2-dimethyl, cis is less stable, but in 1,3-dimethyl, cis one is more stable than trans conformation. Same we can draw these arrangements for 1,4-dimethyl. One 4-dimethyl cyclohexane. One of the interesting facts is that in 1,4-dimethyl there is no chiral carbon, whether it is cis or it is trans. Like suppose if we make it cis arrangement, methyl are on the same side, or we make it trans. In wedge dash projection, this one is trans. You can see that this carbon, two different groups are there, but on both sides CH2, CH2, same. Next atom is same, and this atom is common. The whole group is the same group from both sides. So this carbon can't be taken as a chiral carbon. So 1,4-dimethyl-cyclohexane have no chiral carbon. And there is a plane of symmetry both in cis as well as in trans conformation. You can see in this 3-dimensional model like this. Whether it is cis or trans, it will always have symmetry. You can draw the plane from this side. And there is a plane of symmetry as well as the center of symmetry in trans. From center to equal distance from both sides, you have center of symmetry. So both cis and trans have optical inactivity. In chair conformation, first we draw chair conformation for cis isomer. First atom, axial atom. In second, first one is equatorial atom having hydrogen. Second atom is axial having hydrogen. third atom, first atom will be axial hydrogen, other one is equatorial hydrogen. The fourth one, first atom will be now axial, equatorial, and this is having methyl. Its first bond is axial, its first bond is equatorial, identical group on first bond, so this arrangement is cis arrangement. One axial position is having bigger group, one equatorial position is having bigger group, so it will have identical chair conformations. We are at first carbon. This methyl, which is at axial position, will now be at equatorial position. And at fourth carbon, when methyl is at equatorial position, now it will be at axial position. So both the conformation have same stability. But in its trans conformation, trans configuration, cis and trans are configurations, but these two chair forms are conformations. One axial bond having methyl, first bond having methyl, here the first bond having hydrogen, second bond having methyl. So first bond having different groups, that means this arrangement is trans. Another chair, this axial will now be equatorial and this axial will now be equatorial. Both the bigger groups are at equatorial position, so this is more stable. K equilibrium will be more than 1. So this is all about dimethyl-cyclohexane 1,2, 1,3 and 1,4. This is all about conformation and configuration of cyclohexane.